also ER doc. And Liz Warren here is going to be working with me. She's a physiologist at JSC. She could tell you a little bit more.
Yeah, we figured we'd go ahead and combine our talks because they're probably pretty similar.
Yeah. And I was going to call on her anyway about
and I don't have any slides, so
yeah, so that's
really
all right. Okay, so I know this is probably not a medical audience, so I decided to just give a very brief overview of space medicine, just, a little teaser to get you interested. Yes? Okay.
This is the scary part, where other people touch your presentation.
Oh, that's okay. 3D, wow.
Oh, yeah.
I didn't make it in 3D, though.
Well, now it's going to be presented in 3D. That's the best part. Thank you.
It looks the same to me. Okay. All right. So, this is a space audience, so you don't need me to tell you about Sputnik and Yuri Gagarin and President Kennedy's declaration that we will land a man on the moon and return him safely. But you may not remember when President Kennedy made that speech, America really only had one flight, successful human flight under its belt, and that was Alan Shepard's 15-minute suborbital flight. So, that to me seems very amazing that, we would have such a big goal with very, very little experience. So in the 1940s and 50s, there were all these dire predictions from life scientists and physicians. There was concern that humans couldn't function in space. People said that your heart would stop beating, your muscles would stop working, and you just couldn't act. You couldn't swallow, you couldn't digest food, et cetera, et cetera. That was one of the reasons why there were all these medical tests that were done on the early astronaut applicants that seem kind of barbaric now. But those were kind of necessary because people just didn't know how the human body would function in space. And they wanted to have the best specimens. They had to send a monkey up first to make sure an organism can actually survive in space. So we've come a long way. Not only have we proven that humans can survive and function in space, but astronauts like Sunita Williams have run a marathon in space. Various cosmonauts have set endurance records, which I think is fabulous. They make things look easy, but really, spaceflight is not easy. There's no easy button. So I'm going to talk a little bit about what happens to your body in space. And just imagine you are one of the astronauts, you're launching into space, after years of hard work and so forth, you finally made it. So what happens to you? Well, one of the things that could happen is, I lost a picture. I had a great picture of somebody hurling. So if this is your first flight, chances are you're going to be sick. Space motion sickness affects about 73% of the crew members on their first flight in the first 2 or 3 days, which is why EVAs are generally not scheduled until day 4 or later, just because you don't want people throwing up. And one of the interesting things is that there's no correlation between terrestrial motion sickness and space motion sickness. So you can have an iron stomach on Earth, and you get to space, you're throwing up, and you just can't keep anything down, and vice versa. And so there's no way to predict who's going to get sick and who's not. So that's one of the reasons why NASA doesn't screen astronaut applicants for motion sickness resistance, because there's just no correlation. Feel free to jump in here anytime, actually. So now I'm going to talk a little bit about space.
Actually, I'm going to interject.
Okay.
I need a volunteer.
Oh, okay. We have a volunteer.
I forgot to bring my tape measure for my cool experiment, though. But someone will volunteer.
Okay. All right, come on up.
Since we're going to talk about fluid shift, do you want to do a fluid shift experiment?
Sure, whatever.
How do you feel about laying down on the floor?
I can do it.
But I want your legs up on the wall.
Okay.
How about right here? Looks awesome.
Okay. I don't know if they get with the camera.
You want me to do it over here?
Well, your feet are going to be up on that. You can do it here, maybe. So I'm going to have to kind of fake the measurement aspect because I forgot to bring a tape measure.
Oh, you don't make me hurl on
No.
But we're done with this.
This is something you can do with your friends at home or kids. what we would have done already is we would have measured, picked a spot on your calf, mark it with a pen so we get the same spot. And we're going to leave you here for about 10 minutes.
Oh.
It's going to feel, I know. You consent to this, right? That's what we tell the astronauts to.
Can I still watch your presentation?
Pretty much. So what we would do is we would measure your calf diameter every minute or so, or every 2 minutes. And the other thing, we have phones to do this. I'm going to take a picture of your face right now.
I feel fluid shift already.
Yes, I know you do.
Yeah.
It happens very quickly, but this is, if I had done this properly and thought about this, we would have done a picture of your face before you laid down.
Before and after.
Oh, that's really bright, isn't it? That sucks. Okay, we're going to do this again after Jen's going to continue,
Okay.
and then we'll see if there's a difference.
All right, I actually have a little animation. I call it animation. It's just my stick figures. Kind of illustrating this. So, this is you on Earth, 1G, and Tracy Caldwell-Dyson, our astronaut model here. So this is what you look like in 1G. Now, when you go up into space initially, all the blood and fluid that's usually pulled down to your legs because of gravity is no longer pulled down. So there's a headward shift of this fluid. So initially when you get there, your face gets puffy. And your whole upper body gets more fluid than it normally sees. And your legs, what Liz was saying, your calf muscle, the diameter decreases. So the so-called puffy face chicken leg syndrome. And your body senses this. Your body is very smart. And it senses that there's a fluid overload in your body. So what does it do? It tells your body figures out that you need to get rid of some of the excess fluid and also take in less fluid. So over time, you reach a new equilibrium. You kind of go back to normal in terms of your face and all that. But overall, your volume status is less than what it normally is on Earth. But it's not a problem in space because this is what it needs. The problem comes when you come back to a gravity environment. When you come back to Earth, you have to get up and walk around and do all that stuff. And sometimes you just don't have enough blood volume. And what happens is you pass out. And that's happened before. Especially if you land in Florida or, come back to Houston where it's, 90 degrees, 95% humidity and super hot, that just basically lowers your tolerance even more. So, how are you doing?
He's doing great.
Okay. All right.
There's something I wanted to interject.
Oh,
there
yeah.
that
Go ahead.
You didn't skip, but you
Okay.
glossed over as
Okay.
if you were talking to a crew member. What do you mean there's going to be a new equilibrium? What's going to happen?
Yeah. Well, I'll let you say that.
What's going to happen is
Sure.
you're going to spend about the first 2 days peeing a lot
Yeah.
as well as throwing up.
Right.
So this new equilibrium, your body senses or perceives that there's too much fluid, and there's really cool receptors that they perceive pressure, they measure pressure, and those are all located in your upper body where all that fluid went to. And as a result, your body's going to try and purge some of that fluid because what it thinks is it's got too much blood pressure. That's never good. Your body wants to regulate that very carefully and closely. So there will be a diuresis, or you'll end up urinating a lot, lose some of that volume of blood and fluid in your body, but that's the part where you might end up passing out when you get back to Earth because you've kind of reached a new equilibrium with less blood volume.
Right. Yeah, it's almost as if you were in an accident or something, you lost a lot of blood. Okay, so moving on. So muscle loss is another big problem. Basically your body, like I said, is really smart. It figures out that, hey, if you don't need something, then why keep it up? Muscle is definitely one of the things that could go. You could have significant declines in strength and also decrease in leg muscle volume. And the numbers that we get are pretty staggering. And the scary part is that this is after all the exercise that astronauts do. They spend about 2.5 hours. Well, they get a lot of 2.5 hours a day for exercise. It's not all exercise. There's set up and take down and all that. But they spend a lot of time every day exercising. And even so, we're seeing decreases in strength and muscle volume after their stay in space. And especially the ISS crew members, they come back and most of the time they're not walking the first day, right?
I've actually been extremely impressed with how well
Yeah.
crew members are looking. They are walking the first day.
they are,
of these,
yeah.
Especially now that we've got ARED.
Yeah.
Our crew
Well,
members
yeah.
are looking fantastic. They're ushered out of the space capsule, like that one picture. They're carried, but within hours they're standing and walking on their own.
Yeah. Yeah. So, I mean, you know, but this is something definitely you need to worry about when, say, astronauts are going to Mars. You know, you need to have some kind of countermeasure against muscle loss. Bone loss is another big one, and here's my second attempt at cartoons. So basically, if you imagine your bone, there's like a cortical shell, the kind of the harder outer shell, and then the middle is kind of a matrix of bone that supports that outer shell. And what happens, you know, again, you know, use it or lose it. In microgravity, you don't have gravity basically stimulating additional bone growth. So let me take a step back. So your bone is constantly turning over. So, you know, at the same rate, usually at the same rate that it's being, what's the word? Bone is being broken down and then being built up at the same time. So usually you're at equilibrium, so you're not losing bone, you know, net bone. But in space, you lose the stimulus for building bone. So you're still losing bone's still being broken down, but you're not building up as much. So overall, you start losing bone mass. And, you know, basically you get a thinner cortical shell, and then you also get, you know, decreased bone mass. Yes?
So why does the body break down the bone?
Yeah, it's just how it is. I mean, I'll let the physiology expert explain it a little bit better.
Your bone is largely living
Yeah.
tissue. It's full of blood vessels. There are not very many sensory endings, but there are nerves, and your entire body is constantly being broken down and rebuilt. You know, every cell in your body is under constant transition. So it's just a natural process. And when, as Jen explained, there's an imbalance when you're in spaceflight, when there's not much loading on the bone. There's just as much resorption or reabsorption of that bone, and not so much building up. Bone also serves as a mineral storage capacity unit for you. Basically, there's calcium, there's phosphorus, and magnesium. All of these minerals that your body needs. It's a great storage point, and so your body can kind of lump stuff in there that it'll need in the future. So it needs to be able to access.
Well, bone and muscle are separate, but I mean, I don't know the actual.
Is your
weights.
question
Yeah.
why the rebuilding process is slower in space? Bone, there's a law called Wolff's Law, and it very simply states that bone is as strong as it needs to be, or the more loading on bone, the more it will build. So when you don't put a lot of loading on your bone, in terms of gravity, that provides like a great loading stimulus. But without much force on the bone, there's not much impetus for it to grow. And the cellular mechanisms that cause that growth are all force-based. So if you don't load the bone with forces, you're not going to grow bone.
One last question.
Yes.
Sure.
If you constantly fast,
You will
It'll
grow
hurt.
bonier there.
Yeah.
You know, there's various studies that actually have done things like that. Stand on a vibrating plate that constantly jars your body, and you'll grow bone faster in those, particularly your heel, but the most impacted area, you will grow more bone there.
Yeah, and actually they're looking at using ultrasound to stimulate bone growth, which is basically like very, you know, fast vibration.
You go play tennis, and I'll tell you what, your wrist bone's going to grow.
Yeah. Yeah. So I just want to point out this graph here because it's
One last picture on the way.
okay. It's very telling. So basically what it plots is all the different systems, the changes that they undergo over time. And if you see, I don't have a pointer, but if you see the neurovestibular system, the fluids, they all have this peak initially and then they, kind of tapers down. But bone loss, it's a linear increase, 1 to 2% per month, and it just seems to keep going. We haven't figured out where the plateau is, if there's even a plateau. And, what we worry about is that, fractures could happen because the bone becomes so thin and brittle. So you don't need to be a doctor, but that's broken. So we don't want that to happen, say when an astronaut lands on Mars. So that's just a very quick overview of like the biggest, not the biggest, but the major problems with.
So you tell them why I did that.
Yeah. Okay. So the big problem that could happen in space, but there's like a whole host of other things that could happen just because your body has evolved, to thrive in 1G, and when you go into microgravity, all these things, that you take for granted are out the window. So, talk about physiology, but, psychological issues is definitely an issue. And just because, you're in space doesn't mean all the terrestrial diseases that could happen, you don't happen to you in space. So, as a medical person, I have to basically be prepared to deal with these things. And, for example, how do you do CPR? I was talking to somebody at lunch talking about how you could do CPR in space. And, when you go to Mars, the astronauts aren't going to be able to turn right back around and get medical help if they get sick or hurt. So what kind of capabilities do you need to have on these missions? So that's why I think it's very interesting. And there's also all these operational issues, just how do you keep a human alive in space? There's a lot of research gaps that are going on. People are looking into all these different things, and we can certainly talk about some of these if you're interested. But here's some links if you're interested in learning more about space medicine. And do you want to follow up on your little experiment?
Well, had I done that correctly and I brought a tape measure with me, we would have measured what I perceive to be a dramatic decrease in the diameter of his calves. He probably would have lost about 1 to 2 centimeters in an ideal situation. And his face did get a little bit puffier. And again, in an ideal situation, you do that for a full 10 minutes, and I guarantee it does start to get uncomfortable after a while. But it's something, go home and try it with your roommates tonight.
I can feel like the pressure change in my head after 20 seconds.
Yeah, and your face got a little bit redder as well.
Yeah.
So I say we fill the rest of the time either answering questions or we can pose some of our own questions.
Yeah. Go ahead.
What are decompression?
What is decompression sickness? So if you go back to, I guess, chemistry or physics, there's all these gas laws. So one of them, I think it's Henry's law, it has to do with how nitrogen bubbles can form when you are
Back up 1 second.
Oh, sorry.
Your blood is full of gas.
Okay. Sorry.
Okay, you know that.
Yeah.
So that
Okay.
oxygen transport, CO2
Yeah.
removal.
Yeah.
Okay.
And we live in like a 78% nitrogen, and the rest 21% oxygen environment. So when you go diving, you're at a much higher pressure, and when you start coming back up, when the ambient pressure decreases, nitrogen bubbles can form or come out of solution if the rate of ascent is too quick. So what happens is that the nitrogen bubbles could basically go anywhere in your body. They go in your joints, they go in your brain, they could go into your muscles and whatever, and cause all sorts of problems. So decompression sickness is basically a spectrum. There's type 1, which is the like some skin changes, to type 2, which is more serious. They're altered. They can have stroke-like symptoms, for example. So definitely something that you need to worry about in space, just because when you're going to do an EVA, basically you're changing your atmosphere. You're going from a higher pressure to a lower pressure.
So who here has ever scuba dived?
Yeah.
Okay, so during your classes for scuba, you learn about given temperature, you change the pressure of a gas, the volume will change in an inverse relationship. And a great example of this is you go over in the break room and open a can of Coke. If you were able to see through that can before you open it, you don't see any bubbles in there. It's just liquid. When you open that can, you expose it to ambient pressure. You decrease the pressure on the fluid in there, and that allows I guess it's all carbon dioxide, to come out of solution. Previously, pressure was holding the gases in solution. When you release that pressure, it allows the bubbles to come out of solution, and that causes the fizziness. But if that happens in your body, it hurts badly. And that could happen in your body, and that's what decompression sickness is.
Yes.
Oh, we'll go for the back row first.
Okay, back row first. Oh yeah, for sure. osteoporosis is definitely a big problem on Earth. Osteoporosis, so basically it's, loss of or decreased bone mass. So it tends to happen more in older women, but I mean, men could get it too. And basically, you just, again, it has to do with, changes in the balance of, bone breakdown and, rebuilding. And basically what happens is that, little old ladies get hip fractures when they fall. That's basically, what, causes, not the fall itself, but the osteoporosis part. So, normally if you hit something, if you run against something, you're not going to break your bone. But if your bone gets so brittle, you lose enough bone mass that, that a little minor trauma could cause a big fracture. So, this is kind of what we're seeing in astronauts in terms of the bone loss, but we think there's different mechanisms behind it, and understanding how osteoporosis happens, how this bone loss happens, and figuring out how to treat these in astronauts could certainly be brought back to Earth, and to help all these millions of people, who are at risk for osteoporosis. And just kind of to give you a little clinical perspective. So I work in the ER, and one of the things that we see a lot is hip fractures. So, you have these, 80, 90-year-old people that come in with hip fractures. And for any other reason, if they, say they have heart problems, they need one surgery or another, a lot of times they're not even surgical candidates, just because the risk of surgery and, anesthesia is so great. But if they break their hip, they go to the operating room, just because hip fractures, they're basically bed bound. They could get pneumonia, they could get bed sores, all sorts of things could happen, and their mortality significantly increases, if they have a hip fracture that's not treated. So on Earth, it's definitely a big problem. And if we could figure out how to solve it in space, we could, help lots of people here on Earth.
And I'll add to that, actually. In an inverse kind of relationship, we're actually trying some medications that are used in, Sally Field does commercials for Boniva.
Yeah.
It's very common that there's a lot of osteoporotic drugs out there, bisphosphonates and alendronate. And what those pills essentially do is they try and decrease the rate of resorption. And we're actually trying that in crew members right now experimentally, with actually pretty good results. But surely if we figure out how to prevent bone loss in astronauts, either pharmacologically or with exercise or with some other stimulus, hitting them a lot, I don't know, that may be applicable to old ladies. That sounds totally terrible, but you know what I mean. And this picture shows very good what osteoporosis does. Bone, part of what gives it strength is it's kind of these random sponge-like matrices and connections. And when you start to lose mass in that bone, the spaces between those connections start getting bigger, and the overall structure is weaker, more prone to fracture.
Okay, and you had a problem. Oh, a question, sorry. I'm sorry, I can't hear you. Oh, vision problem. Yeah, it's definitely a very hot topic right now at NASA, just because over the last, I don't even know, like 2 or 3 years, crew members coming back from the ISS have reported visual changes. And a lot of smart people are looking into the problem, just trying to figure out what's going on. And part of it could be due to the fluid shift that we talked about. But there's probably other mechanisms at work, and we still don't know what the problem is. So it's definitely an ongoing research, and I guess stay tuned. No, I mean, cataracts can certainly form. I didn't talk about this, but like space radiation is a big issue, and radiation is known to cause cataracts. But what I was just talking about is basically swelling kind of in the optic disc, and that changing your vision, and that we don't really have a handle on yet. Should I put Mark on the spot? We have a psychiatrist here in the audience. I could start, and then you could jump in. Here, you want to?
Mark, hit the mute so it shows you green. There you go.
Technology, you have to love it. All of them. Essentially, every psychological problem that is known to mental health could occur. They generally fall into two categories. First, imagine yourself locked up in a garage for 3 months with the same group of people. Can you see how they might get on each other's nerves after a while? That's, well, that's pretty much what we're doing. And so people who are on the space station or are on extended missions, they're locked up in a small space with the same group of people. They're cut off from their families, their friends, their normal social environment. Their day in, day out routine is monotonous. They don't get weekends to go off, into the mountains or something like that. This is a very stressful and unnatural kind of environment. What do you see? Well, firstly, you could conceivably see instances of depression and depressive disorders coming up. That's the one that people are mostly concerned about because your astronauts are cut off from their normal environment. You may see personality changes that lead to things like irritability, which make it difficult to get along with each other, and knock-down, drag-out fights, and conceivably, although we haven't seen that. And then beyond that, there are the more subtle performance degradations. People just aren't as sharp as they normally are. They don't do their jobs as well as they normally do. They aren't as quick and as bright as they normally are. And this, of course, is potentially very much a problem. So the question is, how do you prevent that? You do that by screening people. Applicants for the astronaut corps are screened very extensively from a mental health standpoint because firstly, you don't want schizophrenics in your astronaut corps. Beyond that, you want people who just have a history of having strong personalities who function very well. Then, once you have your astronauts, and I think they almost intuitively, the leadership in the astronaut office and in medicine kind of breaks the astronauts down into two groups. The ones who seem to be to do well for short duration missions, such as a 2-week shuttle mission, and the ones who seem to be more likely to do well in the longer duration missions. And these do seem to be two distinct groups. So you choose carefully.
Although that's kind of going away, that distinction.
Is it? Okay.
Well, I mean, just because we don't have a choice. Because if there are no choice, yeah.
Well, this is true too. Yeah. They'll come back someday,
right.
We hope. So you choose people and then you support them. Obviously, it's a lot easier to maintain contact with your families now and with your support system through social media, the internet, email, and the like than it was, say, even 10 years ago. But you want to maintain some degree of contact with the family. Certainly, they have access to mental health support while they're in flight. And then you also want to have some capacity to treat actual out-and-out psychiatric disorders that might occur, such as, say, major depressive disorder and the like. So all of these things are being attended to. But no one really thinks that they've got a complete handle on it yet. There is an extensive literature dealing with the psychology of people who overwinter in the Antarctic, of the people who serve on nuclear submarines that go on extended patrols. All of this is applicable in some way or other to space missions, although no one is exactly sure how, because of course space missions are not precisely like these other venues. But that's pretty much how it's done. Does that answer your question?
Okay. Oh, yes. So many questions.
For who? Yes, go ahead.
Okay.
Yes, please.
So you said like the technos are not as sharp as bright.
I didn't say that. If I did, I'd bite my tongue. I said when you put people into this kind of an environment where they are locked up in a small space with the same people, day in, day out, cut off from their normal social support systems, and expected to function very highly because they have a very complex job, and if they don't do it right, the possible consequences are disastrous. People's performance tends to degrade over time. That just seems to be an aspect of human psychology that in an environment like this, your performance tends to go downhill over time.
Yeah, one way I like to think about this is, imagine, remember the last time you had a cold. You just don't feel very good. So, I mean, you're not going to be as focused on whatever you have to do, as well as you normally would have. So, I mean, this is not, you don't have any physical symptoms necessarily, but just overall, you don't feel like yourself.
So I wanted to ask, so you don't have like, the high form of brightness, I mean, that's some kind of radiation.
It's helpful,
Yeah.
yes, to do different things from one day to the next. Certainly it's nice on your days off to have something to do that's different from what you do day in, day out at your job. But the full variety of human life. We work. We recreate socially, formally and informally. We engage in hobbies. We spaz out and watch TV. Or some of us do.
I spaz out all the time.
We cough. This varied milieu in which we live somehow seems to be important to maintaining our peak performance. And a monotonous, routine environment is one of the things that over time can cause us to not be able to perform up to the level that we could under ideal circumstances.
Can I interject something? So to me, these are doctors, I'm a researcher, so to me, I start thinking, well, how do we measure when peak performance starts to drop off? How do we know when, wow, we really should not be doing an EVA next week because this person is in a slump? We have research tools that we measure kind of cognitive reaction speeds and abilities, simple little computer tests that measure reaction time or how quick they are at simple math skills. So we actually do measure these things as a research project. They're not used operationally yet, so we don't give the information right away to the flight docs and say, hey, is this guy good for an EVA next week? But I think eventually we will get there where information that is collected research-wise will be handed over very quickly to an operational world. Flight surgeon may have access to the data and tell the flight director, let's hold off on that right now.
But that kind of brings up another issue. Something we haven't really talked about yet is astronauts, they are generally concerned with their ability to fly. They want to fly. And a lot of times being a research subject could reveal things that, they might not want their doctors to know. And so it's always this fine line between participating in research and, medical confidentiality and just, whether someone's chances of flying are going to be jeopardized by whatever research experiment they participate in.
I've worked on visualization software used at ESMD, sort of immersive environment type stuff, virtual reality stuff. And it sounds like it's applicable on both ends. One being, I saw a challenge put up on the government site, which was using software for physical interaction, virtual software, virtual environment for physical interaction on long duration space missions, right? So maybe a person could go on a jog and really they're going on a jog through the forest when they're actually in a module somewhere floating through space.
Right.
And it sounds like it's kind of applicable on both ends because the psychological side of that is, okay, if you've got a virtual environment, you could have somebody back at home interacting with someone in a space module. Maybe there's a little bit of lag there, but it's almost like a real world interaction. Like you guys, what's your experience with that?
I actually worked on an experiment such as that with a running basis, having a treadmill that was actually somewhat reactive to a running path. So the crew member would take a camera, go record their favorite running path. Certainly not anywhere around Houston, back home somewhere in some pretty place, and we would program the treadmill to be somewhat reactive with different resistance loads, and that was considered. Let's just say funding-wise, it's kind of like, well, this seems a little frivolous. But I think that there's certainly a future for virtual reality and a little more interactive basis. You know, I think it would be really cool, say, if a crew member has a child, you know, that maybe their wife has a baby. How cool would it be to wear some virtual reality gloves and be able to hold your baby while you're, you know, on your way to Mars? I think that would be kind of cool.
Part of the problem with that, of course, is the size of the hardware and the power consumption. If you want to fly, something, say, on the space station, and certainly if you want to put it on a mission to Mars, it has to meet certain requirements. It can't cost anything. It can't take up any space. It can't weigh anything, and it can't use any power. Well, not quite, but almost.
Right.
I have no doubt that what you're suggesting, absent those constraints, could be very useful. But unfortunately, we can't absent those constraints. So that will affect the usability of what you're describing.
It seems to me, I mean, especially with the cube test and such, the discussion of taking a cell phone, right? We could have an OpenGL capable piece of hardware that doesn't weigh more than a pack of cards with some, I mean, really what we're missing at this point is the visual interface for that. And if you know, tactility, if you want a bonus, but really the visual. I mean, you could get there pretty quick using commercial hardware at this point. I just didn't know if that was even around concept.
I think one other issue, if I want to bring in one other thing that I haven't mentioned yet, in terms of psychological support for astronauts, contact with families and the like, it's one thing when you're doing it on the space station, 2 seconds in communication from Earth. And quite another if you're trying to do it on Mars, where there is, a 20 to 50 minute
20
lag.
each way, probably, yeah.
And so this is each way.
Yeah.
And so, keeping in touch with the folks back home is going to be a very different experience under those circumstances than it is on the space station right now. These are just issues that are kicking around in people's minds that will have to be addressed, certainly, before we actually get serious about going to Mars.
Yeah. Go ahead.
Yeah, a couple of things that I'm interested in. First, how to simulate or recreate the gravitational field like we had in 1G acceleration. That's something
Or artificial gravity.
Yeah, right, artificial gravity, because it seems that one of the big problems is we believe that, and so, I mean, I know if we were going to try to send someone to Mars on chemical propulsion,
It'll take too long.
it would take a lot, so that's one consideration I was thinking of. What is the research being done on that? And the other thing is,
I'll take that one.
Yeah.
I'll give you my next question.
Sure, go ahead.
I have a lot of questions.
Ooh, fantastic.
That's fine.
Well, artificial gravity is one of my kind of favorite pet projects, because we did a bed rest study. Very briefly, if you don't know, one of the ways we can study all these changes that occur in the human body is just put people in bed and basically immobilize them, and we can study a lot of the same changes that happen to astronauts here on Earth with a lot less risk and much cheaper. We did an artificial gravity study just down in Galveston, about a 25-minute drive from here.
Longer than that.
I know.
I drive it every
It
day.
takes a minute. Yeah. So we put people in bed, and we decided, well, we're also going to try this artificial gravity protocol. So we took every other person that was in bed and took them to a centrifuge. And it wasn't like the centrifuge that I think that you probably have in your mind. It looked like you stayed laying down, so you're supine. Your head was near the center of the rotation, and your feet were out toward the outside. So the forces at their head were very normal. The forces at their heart were about 1G toward their feet, just like I am right now. The forces at their feet, though, since it was further out on the radian, was about 2.5G. And so we spun people for an hour every day on this centrifuge. And the results were very promising. We only put them in space, if you will, for 21 days. They were only in bed rest for 21 days. But the results were very promising. We never got the funding to do a longer study. We would have really liked to have done a longer study. So with 21 days, we didn't even see much bone change in the control subjects, the people who did not spin. But we did see a lot of protective signs that this artificial gravity helped their cardiovascular deconditioning, helped prevent that, helped some of the bone marker changes, and even psychologically, these people reported just feeling better with a little gravity load. And so we have a great quote, when you go to Mars, you're going to take your own food, you're going to take your own water, you're going to take your own light, you're going to take your own exercise equipment. Maybe you should also take a little gravity with you.
The other question I had I went to a conference in little more than a year ago where there was a guy from a company that sent salmonella up to the space station and he was developing a vaccine for salmonella. And I was wondering what other kinds of things are being done for Earth-borne diseases by taking them up outside of the bacteria or outside of, well, probably not that part of it, but at least outside of the gravitation.
I don't really know anything about that.
We have seen, there have been studies with salmonella, like you've mentioned, and other kind of bacteria, and we've seen some very promising aspects, although I'm not as familiar with that research either. I know the NASA.gov website has a lot of background and a lot of information on those projects. I'm more of the whole human science, so I actually don't have any of that in the top of my head, but we do a lot of vaccine development experiments, even on shuttle missions, because it's pretty easy to do and simple. But yeah.
Do you have any idea about recreating ozone here on the space shuttle to take care of some of the radiation problem? Gas and gamma rays?
Well, it's not really the ozone that's protective. It's actually the Earth's magnetic fields that are protective. So the problem with shielding,
I think atmospheric.
but for radiation.
Yeah.
Well, yeah,
Well,
UV
it's not the negative space.
Yeah, but I mean it's a combination of the yeah.
space is fire.
Right. So I mean, yeah, yeah. So I mean, I'm not exactly an expert on that, but I know that you know I've seen pictures where they have the fields of magnetic fields from Earth, and basically those kind of repel, so to speak, solar winds and all that. So I mean, I suppose you could have like an active shield around the spacecraft, but that I would imagine would take a lot of power, which we don't have.
Yeah, there was some speculation that maybe it lumpy so there's one of the articles there was a link to some article about generating magnetic field serves as shield around the spacecraft, but I don't.
Yeah, and then you have to wonder too, okay, so you have something that's strong enough to protect the spacecraft. Well, what are the effects? I mean, it's like imagine living in an MRI scanner, like a super powerful MRI scanner. That can't be good for you either. So, you're trading one problem for another. So it definitely, it's an interesting idea and definitely worth, looking into, but I don't know how it would be implemented.
I'd like to backtrack to the question about artificial gravity, too. There seems to be almost like a dance that's going on between the medical people on one side and the engineers on the other side, with medical people saying, hey engineers, it'd be really nice if you could give us artificial gravity for extended space missions. Can you do it? And the engineers say, okay, we'll work on that. They come back a little while later and they say, it's really tough. Are you sure, hey docs, you sure you need artificial gravity? And so the docs go back and talk among themselves, and they go back to the engineers and say, we really, really, really think that artificial gravity would be good. Are you sure you can't do it for us? And back and forth. Artificial gravity would solve an awful lot of medical problems, and it would create an awful lot of engineering nightmares and headaches that would take megabucks to solve. And that's where it stands right now.
Yeah.
It'd be great if it could be done.
Yeah, just to kind of give you perspective. So I heard somebody talking, he was involved with the design of Orion, and apparently there was this back and forth between medicine and engineering about how much water per day can astronauts, have. And they were arguing about 2.5 versus 3 liters a day. So, I mean, that's, for something like water, I mean, I think we all agree we kind of need that. There's a lot of debate about that already. Something like artificial gravity is definitely out there.
Well, water we need, yes.
Yeah.
And all the water that we're going to need in space has to be rocketed up from Earth. And water is heavy, which is why they're recycling their pee, because there's water in there and it's already up there, so it's a shame to waste it, because every drop of water you get from your urine is a drop of water that you don't have to blast up into space.
Yeah. Yes. Go ahead. Oh, animals.
Animal reproduction, yes, we've studied a couple of interesting, we've taken sea urchins and we've seen that sea urchin sperm motility is decreased and due to some little phosphorylation that happens in the tail wiggling around. We've seen fish go through almost entire life cycles, I believe, little cichlids, I think. We've done really interesting studies, actually a Russian experiment with quail eggs, and this is the one that gets me the most. They took quail eggs at various stages of incubation. So they took some that were right out of the bird, and they took some that had been incubated for a few days, and then that had been incubated for a few more days. They launched them all at the same time. And the surprising result was that, yes, some of those eggs hatched normally. It was on Mir space station. They even flew around, crazy as it was. But some of the eggs did not hatch, never incubated correctly. And what that tells me is that there's some important phase of mammalian development that requires gravity. And probably the docs could talk about that one better, but something in the neural tube, I think, may require some gravity signal for it to occur correctly, but I don't know.
Yeah.
That's something that actually we don't know all that much about, although most docs, I think, would tell you, we don't know, but we really, 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 really think that gravity is important. We're not sure how, but we really think it is, and so I wouldn't want to bet that there wouldn't be any problems with human reproduction in 0G, but there's just no database. I don't believe there have been any studies of primates, of primate reproduction in space, and yeah, it's an issue when we talk about building these huge things and sending them off to the next star. That would certainly be a multi-generational experience, and we just don't know. But we really, really, really think that it's important.
Yeah. Well, there's all these questions that we would love to have the answers to. Just funding, time, whatever. We can't pursue all these different studies. So, I think part of spaceflight is, you have to be comfortable with uncertainty a little bit. You try to buy down the risk as much as you can, but, you're not going to be able to know exactly every single thing that can happen, and you just have to accept that. But at the same time, you can't say, you know what, we don't know enough, so we're not going to go. Because, that doesn't make sense to me either. I would say, well, with or without artificial gravity? Without, okay, assuming without. So for me, my list, I don't know what order, but bone loss would be one, space radiation, and probably psych.
And I would say radiation is the big baddie out there, followed by bone, followed by psych.
Sure. I could give you a very brief overview because I'm not an expert on that. But basically, there's two types of radiation. There's galactic cosmic rays. Basically, they think it's from remnants of supernova from outside our solar system. And then there's solar radiation from our sun. So basically, the sun kind of has these, I think, 11-year cycles that there's solar maximums and solar minimums, and at maximums, the sun basically just spews out a lot of high energy particles, essentially, and these, it's a form of ionizing radiation. So anytime these particles, whatever, hit another, hit matter, basically, could cause damage. And for us, living things, the radiation has enough energy to basically damage our DNA, damage our cells. And so, you have to worry about acute radiation syndrome, for example, what the atomic bomb people had to go through. So a big blast of radiation in an acute period of time. But then there's also the chronic changes that you can see. So, you have increased incidence of cancer, cataracts we talked about, and other things. So, radiation is something that we still don't know a lot about. We don't even know how to forecast solar activity very well, and how do we shield, astronauts? What are countermeasures that we could use? If somebody is exposed, how do you treat them? So there's all these things that we still don't know about.
Also, so the high energy radiation that leads to primary but it's also, it's not known, but it's also a question that's being studied basically, so genes that are regions of DNA that contain information, and that DNA, that information is then used in some way, probably that information is then used to, as a blueprint to be able to build a protein. Okay, that, you can say that's manufactured, but genes can't have every gene that is turned on, and so some genes, depending on what cells are turned off permanently, or if they're turned off when their products are being considered. So basically, silent process of turning off or reducing
Did I pause it?
production of that.
I guess I paused this.
Do we know how to think the sun to
How the sun what?
That's got to
Yeah.
be someone more expert here at the sun. Ask
Yeah.
Romeo. He's a sun guy.
Yeah.
Yeah.
I couldn't tell you.
We spent years in school studying other things.
We're not going to turn off the sun. I don't think we
Yeah.
would do that even if we could.
Bad idea.
Yeah.
It's just a product of the nature of the media. In more detail.
Yeah, all right. So I think we had a pretty good discussion going here, and hope we answer some of your questions. But obviously, this is something that's near and dear to all of our hearts here. And, you know, if you have more questions, you can find me around, and hope you learned something. All right, thanks. Thanks, Mark.